Hello class, welcome to the final segment in lecture 17, and in this final segment we're going to talk a bit about the Arctic Oscillation, the North Atlantic Oscillation, and the Madden Julian Oscillation. We're going to briefly talk about those and explain the mechanisms behind that, but the other oscillation patterns, the other patterns that we can have in the atmosphere, that'll be something that you'll explore in greater depth in your radiation climate class in your senior year. But here we're going to briefly talk about some of the Arctic and Northern Atlantic oscillation patterns, the Madden Julian Oscillation, as well as the mechanisms that are behind it. So we'll go ahead and start things off with the Arctic oscillation pattern, and this has to do with the mean temperature found in the Arctic region as well as the mean temperatures found in the mid-latitude region. So you may remember for the hypsometric equation, if you've got cold temperatures throughout the depth of the atmosphere, that means you're going to have heights that are closer, or pressure levels that are closer together, which also tends to give you lower heights. And if you've got warmer temperatures, mean temperatures, which is typical of the mid-latitudes, and you've got relatively high heights, or the isobars are spaced farther apart, and that will typically give you relatively high heights in the atmosphere. And this is typically what you get from the normal pattern. But if you go into the positive phase, which results in lower heights over the Arctic region, this will give you a stronger pressure gradient force, which is also going to result in a stronger jet stream. So in the positive phase of the Arctic Oscillation, you have anomalously low heights over the Arctic region, so you're going to get stronger polar jet stream occurring at around 60 degrees north. But again, that polar jet can vary, its latitude can vary pretty profoundly. And in the case of the positive phase, because the polar jet is so strong, it typically struggles to get to some of the lower latitudes. So that means that in the positive phase of the Arctic Oscillation, you're going to be less likely to get a cold air outbreak in, say, parts of the mid-latitudes, so to some extent the continental United States, but also in Europe and parts of Central Asia as well. So in the positive phase, you got a stronger jet, which is harder to displace southward, which means you're less likely to get a cold air outbreak of some sort. You're less likely to get an intrusion of Arctic air. Versus a negative phase, in which case you have relatively high heights over the over the Arctic, which means you're going to have a weaker pressure gradient force, which is therefore going to give you a weaker jet stream. And this weaker jet stream is a lot easier to displace southward. So in the case of a negative phase, you're going to be more likely to get, say, a cold air outbreak of some sort, or Arctic air spilling down into the mid-latitudes. So positive phase of the Arctic Oscillation, stronger jet, less likely to get cold air outbreaks. Negative phase, where you have relatively high heights over the Arctic, that's going to give you a weaker pressure gradient force, and that's going to give you a weaker jet, which means you're going to be more likely to get cold air or Arctic air spilling into the mid-latitudes. So that's a look at the Arctic Oscillation. The next thing we're going to take a look at is the North Atlantic Oscillation, which has to do with a typical region of low pressure, which usually sits over Greenland, and a region of high pressure, which usually rests near Bermuda or just south of Bermuda, so right around 30 degrees north. And during a typical pattern, which by typical we basically mean the average minimum central pressure for the low and the average minimum or the average maximum central pressure of the high. This is typically what sort of pattern you get. So you get sort of jet stream flow or some sort of west to east flow that travels over much of Central Europe. And this is a pretty typical pattern. But if we enter the positive phase of the North Atlantic Oscillation, the high and the low both intensify, which means we get a stronger pressure gradient force, which means we get a stronger wind traveling from west to east. And this strong pressure gradient will also tend to force the wind farther north. So if you have a really strong pressure gradient force, that means the force also wants to carry the wind farther north, which typically results in the storm tracks also following that wind. So that means you typically get anomalously wet conditions in the northern half of Europe, whereas parts of southern Europe, like Italy, to some extent the Balkan Peninsula and the Iberian Peninsula, it typically is drier than normal during the positive phase of the North Atlantic Oscillation. And if you look at the negative phase, which is basically the weakening of the pressure gradient force, that's going to not only weaken the strength of the flow, so the flow is going to be weaker, but the flow is also going to be displaced further south, which means you're going to have drier conditions in parts of northern Europe, so parts of Scandinavia, United Kingdom, the northern coastline. That's going to typically be drier than normal, and in the southern half of Europe, which again, the Balkan area, the Iberian Peninsula, and Italy, it'll be wetter than normal during the negative phase of the North Atlantic Oscillation. And the last thing that we're going to cover during the course of this lecture is the Madden Julian Oscillation. Now, you may remember back from the second segment, I said that most oscillation patterns are biphasic, which basically means there's a positive phase or a negative phase. Madden Julian Oscillation is kind of interesting because there's actually 8 different phases considered in the Madden Julian Oscillation. And the phases are determined by the longitude of where the oscillation actually is. And the Madden Julian Oscillation itself is just an area of concentrated and more active convection that travels around the equatorial region. It travels around the globe like you see on the screen here. So by active convection basically mean a lot of extra thunderstorm activity occurring near the equatorial region. So we'll say it's here, and then it encircles the globe about every 1 to 2 months, every 30 to 60 days. So later on in time, and it may be, let's say, in the equatorial regions of Africa, then it might wind up in the equatorial regions of the Indian Ocean, and then just continues encircling the globe. And the phase of the Madden Julian Oscillation is determined by what longitude the concentrated convection actually is located. And I'll go ahead and get rid of the bender so you can see the rest of this. So you can see how this pattern can basically just encircle the entire globe here, and typically that it circles the globe about every 30 to 60 days, so about every 1 to 2 months. And this can also have significant impacts on the overall weather pattern, because if you have all this extra convection going on, then you can have some degree of cooling, and if you've got convection going on that's not going on some other part of the world, then you could have, say, more warming of the warm waters, or more warming of the waters, which can influence the location of jet streams and also influence things like hurricane formation and stuff to that effect. But Madden Julian Oscillation, again, it's just basically this area of more active than normal convection, more thunderstorm activity than normal that just encircles the globe. And unlike the other oscillation patterns where it's 2 phases, a positive phase and a negative phase, Madden Julian Oscillation has 8 recognized phases. And again, those phases are determined by the longitude where this area of more active convection is actually concentrated. So that's going to do it for Lecture 17, a look at weather, climate, and some oscillation patterns. So with that, I will go ahead and conclude Lecture 17, and I will see you all in Lecture 18, where we will talk a little bit more about cyclones. So I will see you all there.